Okay, so welcome again. Today we are going to talk about syllogisms. A little cold out here. So last time we talked about conditional expressions and conditional arguments. We talked about the antecedent and the consequent. We talked about unstated and hidden conditions. And we talked about valid and invalid argument forms of conditional arguments. You remember denying the antecedent and affirming the consequent and so on, right? So this is very important. It's good for you to know because you can use this knowledge to judge whether arguments are valid or not without even understanding what the argument says. This is why this is great, right? This is why it's a good thing to know. So today we are talking more about necessary and sufficient conditions and then about categorical syllogisms and what can go wrong with them. And this is another way of determining whether arguments are good or not. So this is whether arguments are valid or not. So this is another very important tool if you want to judge the validity of particular kinds of arguments, then this is what you would use. So let's begin with necessary and sufficient conditions. A necessary condition is one which must be true in order for something else to happen. But still, even if it is true, the consequent also might need other conditions to be fulfilled in order to happen. So it is necessary, right, in the sense that the consequence cannot happen without it, but it is not sufficient. It cannot alone bring about the consequence. This would be something like, if I study, then I will pass my examination. So if I study is a necessary condition, because if you don't study, it's unlikely that you will pass your examination. It's, let's say, impossible to pass the examination. This must be true, otherwise you will not pass the examination. But even if you study, you might fail for other reasons. So studying alone doesn't make it sure that you will pass the examination. You might be sick at the time of the examination. You might be drunk. You might be in love. You might have any other condition, why you will not go to examination, and perhaps you win $1 million in a lottery, so you don't care about the examination anymore, right? So this is then necessary for you in order to pass the examination, but it alone cannot guarantee the result. So the condition is necessary, we say, but not sufficient. If I eat 10 cheeseburgers, then I will be sick. If you eat 10 cheeseburgers now, is a sufficient condition for you to be sick. You don't need anything else. This alone will be enough to make you sick. This is the difference from the necessary condition. At the same time, there are many ways to be sick. Eating 10 cheeseburgers is not the only way to get sick. Let's say you drink 2 bottles of vodka, then you would also be sick, or perhaps even one or half bottle, right? Whatever. You can, eating 20 blocks of chocolate will make you sick. So, all kinds of things. So therefore, drinking dirty water, from the street will make you sick. So there are many ways to get sick, and it's not necessary to eat 10 cheeseburgers. Right? So this is different from necessary, but it is sufficient. This alone can make you sick. You don't need any other conditions. So if this is true, then the consequence will also be true. Nothing else besides this condition is needed to bring about the consequence. So it's very important when you evaluate conditions to be clear about whether these conditions are necessary or sufficient, or perhaps both, right? So you can say, if I have a driving license, then I can drive. If I have a driving license, then I can drive. This is a necessary condition. You need a driving license in order to drive. But it's not a sufficient condition, because with a driving license alone you cannot drive. You also need a car. So the car is also a necessary condition. If you don't have a car, you cannot drive. But alone it is not sufficient, because you also need the driving license. So you have 2 conditions that only together can bring about a result. Each one is necessary, but none can bring about the result alone. Now, this is what the second part of this graphic shows. If you don't have the driving license, then you cannot drive. It doesn't matter that you have a car. And the same with a car. So each one of them is necessary, but not any one of these conditions can alone bring about the result. This is different with sufficient conditions. Now you have two sufficient conditions. If I eat too much, or if I get drunk, then I will feel unwell. And in this case, each one of these conditions alone can bring about the result. If I don't get drunk, eating too much is enough, to bring about the result of feeling unwell. Okay, eating too much is alone enough. I don't need to also get drunk. These are sufficient conditions. So make sure that you look at it again, perhaps. Make sure you understand the difference between necessary conditions and sufficient conditions. And obviously conditions can also be both, right? Necessary and sufficient at the same time. So when you want to judge what condition you see in front of you, first you look at the result. And you think, can I have the result without the condition? If I cannot have the result without the condition, then the condition is necessary. If I cannot have the result without the condition, then the condition is necessary. If the condition alone is sure to bring about the result and I don't need anything else, then the condition is sufficient. And conditions can be both, right? So you can express this as a conditional statement. If A is necessary for B, then think about it for a moment. How would this be in terms of an implication? If A is necessary for B, then how would the implication look like? Is it A implies B or B implies A? Stop the video for a moment, think about it. Okay, so if A is necessary for B, then if not A, then not B. Right? If not A, then not B. Because A is necessary for B. If I don't have A, then I cannot have B, because A is necessary for B. Okay? This, so far, it's easy. But also if B, then A. Why is that? Why is it that if B, then A? B implies A, you could say. Right? Why? Because if A is necessary for B, then I cannot have B without A. So if I now have B, I know that I must have had A. Okay? If B, then A. Let's say a fire is necessary for smoke. A is the fire, B is the smoke. So now if I see the smoke, then I know that I've had a fire. If A is sufficient for B, then if A, then B. Because A alone always brings about B. If A, then I must also have B. Or, if not B, then not A. If I don't have the result, then I don't have A. Because A is sufficient for B. So if I had A, I would have B. Right? If I don't have B, then necessarily I don't have A. Okay. So then this brings up the following question. If A is sufficient for B, then if A, then B, this is what we just said, or if not B, then not A. So it seems then that if A is sufficient for B, A implies B, and not B implies not A are equivalent. This is what follows from the statements above, right? A is sufficient for B, we said, means if A, then B. A implies B. And this is equivalent to if not B, then not A. If not B, then not A is the second thing down there. Not B implies not A. Okay, so then these two should be equivalent. Now, can you prove that these two are equivalent? How can you do it? You can make a truth table. So try to make a truth table now to show that A implies B and not B implies not A are actually equivalent. Okay, stop the video here, make a truth table, show that these two are equivalent, and then we'll meet again. Okay, so I don't make this truth table here you can do it yourself. I mean, you should be good enough now with truth tables to make such a simple truth table. You expect it to have 4 lines, right? A and B, 2 variables, 4 lines. Put everything into one table, only then can you see if they're equivalent, or put them to different truth tables. And then you should clearly see that they are equivalent. If they are not, or if you have any other problems with that, then ask me at the corresponding tutorial section for this lecture. Okay? So which now are necessary and which are sufficient? If you eat a lot of rice, you will not be hungry. You have to take a general education course in order to complete your studies. If you walk in the rain without any protection, you will get wet. If you print out that email, you can read it at home. And if you have a tea bag, you can make some tea. Look at these and tell me which of these are necessary and which are sufficient. So stop the video here again and think about it for a moment, and then we continue. If you eat a lot of rice, you will not be hungry. Sufficient. This condition alone brings about the result. You don't need anything else. You have to take some common core courses in order to complete your studies. Isn't necessary. You have to take the common core courses in order to complete the studies, but just alone taking these courses is not going to let you complete your studies successfully, right? You also need to take some other courses. So this is necessary but not sufficient. If you walk in the rain without any protection, you will get wet. This is sufficient. Just doing that guarantees the result. If you print out that email, you can read it at home. It's sufficient. And here we always assume, that the rest of the world is in a normal state. So we assume that you, for example, you are not blind, right? Or that you can read. So if you don't mention any special other conditions, then we assume that the rest of the world is in a normal state that will not interfere with this process you are describing here. And finally, if you have a tea bag, you can make some tea. This is not necessary and not sufficient, right? This is neither. Because with a tea bag, I cannot just make some tea. I cannot just, eat the tea bag or suck on it. I need also some hot water, and I need a cup and so on. So the tea bag is not sufficient, right? It's not sufficient alone. I need hot water, I need a cup. But is it necessary? Is a tea bag necessary for tea? No, it's also not necessary, because instead of a tea bag, I can have tea in another form. I can have this Japanese tea powder, or I can have tea in loose form that I can put into my cup. Right? Or I can have some instant tea or something that dissolves in the water. So there are all sorts of tea that are not tea bags. And therefore, the tea bag is neither necessary nor sufficient, right? I can have tea leaves instead of a tea bag, and I still need hot water. So it's not necessary, it's not sufficient. Make sure you understand this. So not all conditions need to be necessary or sufficient. Many conditions are neither necessary nor sufficient. They are just conditions among other conditions. And some conditions are both necessary and sufficient. And when they are both necessary and sufficient, then you have a co-implication, a biconditional, between the condition and the result. Right? Because you remember, a necessary condition is an arrow back, and a sufficient condition is an arrow forward. So if you have both necessary and sufficient, it goes both ways. You have a biconditional. So there is an explanation here about if and only. I don't want to go into that now. This is only if you have ever asked yourself, what does only if mean? If it doesn't say if and only if, but if you say only if, what is this exactly? And there is a discussion here to explain, how the only if is different from the if and only if. But I don't think that we necessarily need this for this class, right? So if you just always remember to translate the biconditional as if and only if, and you never use only if, then you will never get into any problems like that. So I still give you this page here. You can look at this, and if you want, stop the video here and try to think about this. But this only complicates things for us, and we don't need this at this moment. Okay, so just ignore that. This is only for your interest. Sometimes, we have some little more advanced topics also with a justification of the implication. Why is the implication truth table like that? I will ask you this. You can, if you're interested, you can look it up. But if you're not interested, you can forget about it, right? And this is the last page of this, Betty and the Apples. This whole thing is an explanation from Wikipedia. You can find more explanation about this in Wikipedia. Okay, so let's jump away from all these things, and now we go to the a more philosophical point about possibility and necessity. So what does it even mean that something is necessary? It's easy to say, A is a necessary condition for B, but what does it really mean? When is a condition necessary for some result? And you see that we have different types of possibility and impossibility. If I say it is impossible to be a tall man without being tall, this is a different kind of impossibility from saying it is impossible to dissolve gold in pure water. This is different from saying it is impossible to travel from Hong Kong to New York in less than 10 minutes. And this is different from saying it is impossible to visit the doctor without an appointment. Think about it for a moment and try to explain in what sense are these different impossibilities different. Think about it for a second. Stop the video, let's continue in a moment. So, you can say it is logically impossible to be tall without being tall. It's not even thinkable. You cannot think of a tall person who is not tall, right? It doesn't make any sense. There is no possible universe in which this might be the case, that somebody who is tall is not tall. On the other hand, it's empirically, physically, causally impossible to dissolve gold in water, but there might be another universe with different physics in which this is possible, right? We can think of a universe like that. You could write a book, fantasy book, like Tolkien, The Lord of the Rings, that plays in another universe, and in this there is some magic that dissolves gold in water. But you can never write a book in which tall people are not tall, right? This, even with magic, this is impossible. It wouldn't make any sense. If they are not tall, then they are not tall, right? So magic can overcome, in a fantasy tale, physical limitations, but it cannot overcome logical limitations. And to travel very fast is currently technologically impossible, but it's not physically impossible. I mean, a beam of light or a radio wave will go from here to New York in less than 10 minutes, right? No problem. So, or if you have a phone and you speak into your phone, your voice arrives in New York. If you call somebody in New York, arrives in less than 10 minutes. It arrives in fractions of a second, right? So, to travel very fast is currently technologically impossible, but it's not logical, it's not physically impossible. It actually happens for things other than humans. For example, electrons can do this, and your voice can do this, and light waves can do it, or light particles, whatever. So it is impossible for us now, but it is perfectly possible, not even in a world with magic, just in a world with a little better technology. More advanced technology. So you could imagine in 100 years, perhaps we can travel to New York in 10 minutes. We will get into some kind of rocket and fly through the stratosphere, and in 10 minutes you are in New York, right? There's no good reason why this should not be possible. Or you will be transported like in Star Trek, your body will dissolve and you be beamed up to the other side, and there you are reconstituted, and then you are in New York, right? So there is no reason why this should be totally impossible, right? It's currently impossible. Now we cannot do it, but in some point in the future we might be able to do it without having to assume that any magic happens. And the last example it's only legally impossible. Let's remember briefly. It's impossible to visit the doctor without an appointment. This was the last one, right? So this is only legally impossible. It's not even impossible, really. It's only. Let me go a little back into the sun because I'm freezing. It is not even impossible to visit the doctor without an appointment. Let's do this. Oops, sorry. Yeah, now it's much better. Now I'm sitting in the sun. So it's. Not impossible to visit the doctor without an appointment. It's impolite, inconvenient. It will be made difficult. People might want to stop you from going to see the doctor. But with some persuasion, if you say, I'm dying, I really need to see the doctor right away, then you will probably manage to see the doctor without an appointment. Or if you have a gun, let's say, right, you go to the doctor and say, I want to see the doctor or I shoot, then you also get to see the doctor without an appointment. So it's not really impossible. It's just a little harder than with an appointment. So these are different degrees of impossibility, right? So make sure that you understand that we have logical impossibility, empirical or physical impossibility. We have technological impossibility. We have legal impossibility. Well, we have, perhaps practical, everyday impossibility, but these are different ways for something to be possible or impossible, and you need to distinguish between them. And correspondingly, we also have different kinds of necessity, right? Things can be necessary in different ways. So, for example, having 4 sides is logically necessary for something to be a square, or having 3 sides is necessary for it to be a triangle. This is a logical necessity. We cannot imagine a square. We cannot even imagine it, right? It's not like one day squares will be discovered that have 3 sides. This is crazy, right? It's not even logically thinkable to have a square that doesn't have 4 sides, because if it doesn't have 4 sides, it's not a square. It's like thinking of a tall man who is not tall. Being a father is logically sufficient for being a parent. So here now we have sufficiency, right? Logical sufficiency. Being a father is logically sufficient for being a parent because being a father automatically, logically makes you a parent, right? You cannot be a father without being a parent. Not even in a science fiction world, not even with the use of magic. The presence of oxygen is causally or physically necessary for the proper functioning of the brain. Now, this is a necessity that applies to Earth and to human brains, but we might imagine that alien brains might exist on some other planet that work without oxygen. They work by, utilizing some other gas or some other chemistry entirely that is not dependent on oxygen, right? In the same way, for example, like a computer, right? In a sense, a computer fulfills many functions of the human brain, right? It is able to do calculations and things, and it doesn't require oxygen. Computers work perfectly well in a vacuum. So this is only a physical kind of accident that our brain requires oxygen, but is not a necessity, right? And it is not it's a physical necessity. It is not a logical necessity. Passing current through a resistor is causally sufficient for the generation of heat. Now, this is if you're not so much into physics, just ignore that, right? But current, electricity goes through a cable, and the cable resists the passage of electricity, and then heats up. This is what happens in these old-style lamps. Light bulbs, and this is sufficient, but it's a causal, it's a physical sufficiency. The rules might be different, and they are actually different. For example, in extreme temperatures, if you have an extremely low temperature, then or extremely high temperature, then you have different states of matter in which these things might behave differently, and they do, right? So being an adult of over 18 years old is legally necessary for having the right to vote. This now is a legal necessity. It is not physical or logical. By changing, our electoral laws to vote when you are 16 or 14 or 4. It wouldn't make much difference with the quality of the result, probably. This would be possible without violating any laws of physics or laws of logic, right? It wouldn't be logically impossible or anything like that. So this is only a legal stipulation, right? And the presence of a witness is legally necessary for a valid marriage. Again, we could easily change that marriages can be performed without a witness, and then we wouldn't be violating any laws of physics or anything like that, right? Okay, so other types of necessity are also possible. This is not an exhaustive list, right? These are the most common ones, but we can easily imagine other types. For example, necessity from morality, politeness, prudence. You can say it's morally necessary to tell the truth. Let me go back a little again here, because now I'm frying in the sun. You see, it's a little difficult when you're outdoors to be entirely happy with the physics of temperature. Much easier in an office, right? So anyway, so you can imagine there is a morality, moral rules, and something might be necessary following particular moral rules or rules of politeness. It's necessary to greet your grandmother when you visit her in her home from politeness, but it's not, of course, a physical or even legal necessity, right? Okay, so there are many kinds of necessity. This is not an exhaustive list here. So let's do an exercise again. Which kind of necessity or sufficiency do you see here? I just give you a few of these here. A recent photograph is, and now you're supposed to say whether it is necessary or sufficient, and whether it is, there are two things there, or whether it is physically, causally, logically, legally necessary or sufficient. Okay, so whenever you have two lines, then you're supposed to say two things. Okay, stop the video and come back in a moment. A recent photograph is legally necessary for a new ID card. Eating 20 mooncakes is causally sufficient for me to be sick physically, right? Having committed a serious crime is legally necessary for going to jail. Owning a cat is logically sufficient for being a pet owner. Fuel is causally necessary for my car to move along. Being a father or mother is logically necessary and sufficient for being a parent. So some conditions can be both, right? I said it in the past already multiple times, but we never had an example, so here's an example. Being a father or a mother is logically necessary and sufficient for being a parent. So you cannot be a parent without being a father or a mother. You cannot be anything else. So it's necessary that you are a father or a mother for being a parent. And it's also sufficient. The moment you are a mother or a father, you are already a parent. So this is necessary and sufficient. Is a biconditional condition between the two, right? Okay. So that's it so far with necessary and sufficient. I hope you are sufficiently happy with that. And now we will change. We will talk about categorical syllogisms, which is a totally different topic, but sometimes we have to stick multiple topics into the same presentation because they are shorter than one session. So now let's talk about something entirely different, categorical syllogisms. Now, why do chickens have feathers is one question. Because they are birds and all birds have feathers. And this is a way to answer it, how the philosopher would do it, right? Because they are birds and all birds have feathers. So you see what's happening here. I'm answering the question by pointing at properties of the class of things we are talking about, the category. So then I get this kind of syllogism. Syllogism means a formal argument. So I get this kind of argument here. All birds have feathers. Premise 2, chickens are birds. Therefore, conclusion, chickens have feathers. And I'm talking about categories of things. I'm talking about birds. Chickens are birds. And all birds are feathery things. And because I'm talking about categories of things, I call these arguments, these syllogisms, categorical syllogisms, because they are syllogisms about the categories of things and the properties of categories. So when you deal with categorical syllogisms, you will see that you cannot very easily use propositional calculus to represent them. It doesn't make much sense to say all birds are feathers is P, chickens are birds is Q, and then conclusion, therefore chickens as feathers is R. If I do that, this is how we do it until now, right, with propositional calculus. But this doesn't help you, because now if you try to write it down formally, it will look like in the second part here P, Q, and then therefore R. But for this you cannot see anything, right? You cannot see if this is correct or not correct, because I can easily make such syllogisms that are wrong, right? And how do we see that they are wrong? So, for example, here I have another example, right? Every lion is a mammal. No fish is a mammal. Therefore, conclusion, no fish is a lion. This is a good syllogism, right? It's valid. This is valid. No problem. But how do I know it's valid is the question. All students have a student ID. Some people have no student ID. Therefore, some people are not students. That's also valid. But how do I know? So you see, we need a new tool, a new mechanism to show whether such syllogisms are valid or not. And in order to do that, we need to realize that these syllogisms always have the same structure, and we can take them apart in a specific way, always the same way. Look at the structure, right? You see on the right hand, in the first example, every something is a mammal. No something is a mammal. You have the same word mammal 2 times, and then in the conclusion you combine the 2 first words, the lion and the fish. The second is the same structure. All students have a student ID. Some people have no student ID, student ID, student ID, and then in the conclusion you take the students and the some people and combine them together. So realizing this gives you now a tool to examine these things by taking them apart at these blocks, like Lego, right? So you would say, I can take this apart. First I have 2 premises and a conclusion, clearly, right? 2 premises. Premise 1, every lion is a mammal. Premise 2, no fish is a mammal. Conclusion, no fish is a lion. But now the 2 premises are connected by this common term, which we call the middle term, which appears in both but not in the conclusion. All students have a student ID. Some people have no student ID. So student ID now becomes the middle term. It's the term that is present in both premises but not in the conclusion. Same with the next. Every lion is a mammal. No fish is a mammal. Therefore, no fish is a lion. Mammal is the term that is present in both premises but not in the conclusion. The conclusion now itself, if you look there, has a subject and a predicate, a property that applies to the subject. Some people are not students, some people is the subject, and these people have a predicate, they have a property that applies to these people of not being students. And so some people is the subject, are not students is the predicate. The same here again. No fish is a lion, fish is the subject, and being a lion is the predicate. So no fish have the property of being a lion. Now, the subject of the conclusion is called the minor term of the syllogism. It's just a word. Just, instead of saying subject, you say minor term sometimes, and the predicate is called the major term. So don't be afraid of these words. It's just because this whole thing with the syllogism, this started with Aristotle. And since Aristotle, we have had 2,400 years of 2,300 years of logic. And in these 2,300 years of logic, people have worked with these things more, with these tools over time. They have developed different theories about them. And so the words have changed, and the words have developed, and they have developed new terms for them, and so on. And so subject and predicate is a grammatical term, while minor and major term is a term from logic that applies particularly to syllogisms. So we need to be comfortable with both, because we are at the end of this long tradition, right? Okay, so no fish is a lion, some people are not students. These are the 2 conclusions we had, and you see the minor term now is always in italics, and the and the predicate is in boldface. So now let's do an exercise. Find in these two different syllogisms now the major, minor, and middle terms. If you cannot do it, go back, listen to the previous 2 minutes, and then come back here, and then do this again. Okay, stop here for a moment and try to do this exercise. Okay, so what are the major, minor, and middle terms? Here the major terms are bold, mammals, sweet. The minor are pets and presents, and the middle terms are dogs and cakes. The middle terms, you should probably always begin by identifying the middle terms is easiest, right? The middle terms are the easiest. They are the term that is in both premises but not in the conclusion. You can easily spot dog, dogs, cake, cakes. And then you look at the conclusion itself. What are the things that have a property? The pets have the property of being mammals. The presents have the property of being sweet. So, therefore, this thing that has the property is the subject, and the property itself that the subject has is the predicate, and this then is the major term. Okay? So now, with this analysis here, we don't yet know whether our syllogisms are valid. We just know how to take them apart. So now you can use a tool called a Venn diagram, which is a lot of fun and entertainment, and you can do it graphically. It involves, drawing circles. And no, I mean this seriously. So this is a fun thing where you can find out whether these syllogisms are valid. You just need to concentrate for a moment to understand how this tool is used. If you know how to use it, it's very useful. It's a lot of fun. It's very easy to do. Just try to learn how to do it correctly. A Venn diagram represents a syllogism graphically, and it involves 3 circles always. You can in principle have diagrams with more circles, but we will do only 3. So you have the subject, the predicate, and the middle term, and we try to write them down in this way always. Subject on the top left, predicate on the top right, middle term at the bottom, and all should intersect each other. So you need to make sure that when you draw them so that you have the intersections like you see here. Okay, they should intersect in this way. So you altogether you have 1, 2, 3, 4, 5, 6, 7 different areas, right? Make sure you count 7 different areas that are delimited by lines. Okay, each circle represents subject, predicate, and middle term. Now, the rules for drawing this thing is, if a circle is empty, we don't know anything about it, or if an area is empty. Like here, P or M outside of the area where the X is, just the area of the M, not the whole circle, but just this area where the M is inside, right? This, we don't know anything about it, so it's empty. Wait a moment. I mean, you will ask, what does it mean it's empty, and what does it mean we don't know? Wait a second. You will see it in a second. Okay? Be patient. Second, if it is shaded like top left the S, if it is shaded like the S, then there are no elements in it. This is different from, how you would normally think. Normally when we shade something with a pen, we mean there is something there, which is the shading. But here the shading means there's nothing in there. Okay, this is just a little counterintuitive. So when you shade it, it means there's nothing in there. When you do it by hand, you can shade it by drawing lines close to each other, right? You hatch it in a way. So you don't need to shade it, like with a watercolor or something. You can do it with your pencil. You draw lines to shade it. So this means there is nothing in it. If there is no shading in it, then it means I don't know anything. If it's actually empty, then you shade it, okay? And if it contains an X, like this little area between P and M in this example, then there is at least one thing in that category. And these are all the rules. There is no more to it, right? That's all. Remember these 3 rules. And now, what you do, when you have a syllogism is to draw the right representation for the premises into your Venn diagram, and then to look if the result is consistent with the conclusion. This is the main way of doing it. You draw the premises, you don't draw the conclusion, you just look if the conclusion, after drawing the premises, if the conclusion is consistent with your drawing. If it is, then the syllogism is correct. If it is not, then the syllogism is invalid. So let's see how to draw the premises. If I say something like all lions are mammals, what do? All lions are mammals. All S are P. All S are P. All subject are predicate. Since all subject are predicate, there cannot be any subject that are not predicate. So therefore, there cannot be any lions that are not mammals. So the lions are my S circle, the mammals are my P circle. And now I know that there is no S which is not P, and therefore I shade the S that is not P out. By shading it, I say it's empty. You remember, right? Shading means it's empty. So now I shade it, and therefore I show the S outside of the area of P is empty. There are no lions that are not mammals, therefore equivalent to saying all lions are mammals. This is the representation of all lions are mammals in a Venn diagram. Make sure you understand that. If you don't understand that, go back and listen to the past 2 or 3 minutes again to make sure that you understand that. So the next one, some S are P, some cats are black. You have this kind of Venn diagram then. Some cats are black says that there are some things, some subjects that are predicate. So if you talk about some, this means you want to say there exists a subject that is predicate. You are not talking about all or none, so you're not going to shade anything. You are going to say there is something, and there is something is represented in a Venn diagram by an X, right? An X. So I have to put an X somewhere. Where do I put the X? Some cats are black. Between the subject and the predicate I put my X. But now the question arises, so where the X is there, right, in this graphic. But we don't know where exactly the X goes, because it could go to the upper part that is outside of the middle term, or where the 1 is now, or it could go where the 2 is now, which is inside the middle term. If I only know some cats are black, and I don't know the middle term, because in this example now we don't have a middle term, we have only one premise, some cats are black. So therefore I don't know whether it goes. Is it in the middle term or outside of the middle term? Therefore I draw it right on the line where the X is. So if you cannot decide whether it goes into 1 or whether it goes into 2 because you don't have a middle term or because the middle term doesn't tell you where it goes, then you just put it on the line. And putting it on the line signifies that it possibly belongs to both areas. Okay? Sometimes you can avoid this by shading the all areas first, like the previous one. All lions are mammals. By shading away the S, you know that it cannot be in a particular area. It cannot be in the S anymore. So then it might be easier. If you had shaded, for example, the middle term already, then you would know it cannot be 2, because by shading it you say there is nothing in the area of the middle term, therefore 2 is impossible, so it must be 1. Okay? In this example. So shading first will remove, painting the all terms first, which allow you to remove areas, to shade them out, will remove this ambiguity. So this is why when we make Venn diagrams in real life, we first do the all statements. We don't do them in the order of the premises, but we do the all statements first, and then we do the sum statements. Because the all statements will remove parts of the graphic, so that then the sum statements will be possibly less ambiguous, because there are less places for the X's to go. Okay? Yeah, don't worry now, if this sounds complicated, you will see it in a moment. So some cats are not black. Again, this is a sum statement. So now, with sum statements, we always have an X involved. So some cats are not black means I have an X that is outside of the predicate, because the predicate is black, right? So I have an X that is outside of the circle of the predicate, And again, I don't know if it goes inside or outside the middle term, so therefore I will just put it on the line. And finally, no S is P, no taxi drivers are bus drivers. This is saying I have the taxi drivers in the S circle, I have the bus drivers in the P circle, and there is no common ground between them. Therefore, the area where S and P overlap must be empty, because no taxi drivers and bus drivers, there's nothing in there. Okay, so it's empty. You hatch it away. So these are the basic rules, that's it. And now you can use it to prove that these things are correct. So for example, all lions are mammals, all M are P, some rare animals are lions, some S are M, some rare animals S are P. Try to prove that this is correct with a Venn diagram. Stop here, try to do this, and come back in a second. Okay, in order to prove this, we would first shade the circles according to the premises. First, shade. Then you would see whether the resulting shading is consistent with the conclusion. This is how you do it, always. In every Venn diagram. First, you shade and put the X's according to the premises, and then you see whether the resulting shading and painting is consistent with the conclusion. Always shade all sentences first, because this removes the ambiguities, right? So, all lions, M, are mammals, P. What do I shade? I shade that. Because all lions is my middle term. You see, the middle term also appears in the second premise. Lions. And all lions are mammals. P. The mammals are P. If all lions, if all M are P, then there are no M that are not P. So all M must be in the area that is also covered by the P, the common area. This means the area of M that is not P must be empty. And this is why I can shade it. So that's my first premise. Think about how to make the second premise now. Some rare animals are lions. Here it is. Some S are M. Some S are M. And now you already know that the left part is shaded, so it cannot be there. This is why it was good to do the all first. Otherwise, you would not know where the X goes, into the one or in the second boxy there, right? But now you know that the left part of this area is shaded, so nothing is in there. Therefore, the X can only go into this area, so this contains an X. And now I've shaded, I've painted, I've drawn my premises. And now I can ask, is this consistent with the conclusion? Some S are P. Is this consistent with the conclusion? Yes. Some S are P is exactly where the X is. So the argument is valid. These X are exactly the S that are P. These are the rare animals that are mammals. So you don't shade the conclusion, you just check it against the shading of the premises. If you also drew the conclusion, then it would be pointless, because then you would make the conclusion into a premise, right? Then it would always be valid. So the point is to see, is it valid if I don't draw the conclusion, if I just check the conclusion against the drawing of the premises. The two must agree, and then the thing is valid. So now it's valid because I have the X where I need it in order to draw the conclusion. Okay, try another one. No fish is a mammal, some mammals are animals, therefore some animals are not fish. Do it yourself, stop the video, do it, return in a moment. Okay, so let's go. Here we are. This is your drawing as it should look like. The first premise is the shaded area. No fish is a mammal, no P is an M. If no P is an M, then the area between P and M must be shaded, means no, empty. Second, some mammals, some M are S, are animals, some M are S, then I have to put an X between M and S, and because half of that is already shaded, it cannot be in there, so it's in the other half, like here. And therefore, the conclusion now, some S are not P, some S are not P. There they are, where the X is. These are the S that are not P, right? Therefore, this is valid. So here, a little explanation. Some people sometimes ask me, why this is right, and on the left side, and not on the right side, the s that are not p, some s are not p. Why don't we take the whole s to be a solution? And the answer is not the whole s is a solution, because we also need to show that there is something in there, and so we need to take the area that contains the x. This is the solution, because these are some animals that are not fish. They are represented by the x. The other subject area that is not that area with the x on the right of this picture, we don't know if this contains anything. It might be empty, then I wouldn't have anything. Because if I don't draw anything, I don't know anything about it, right? There might be things in there or not. While where the x is, there I know there is something, and this is the something I'm talking about. Some animals that are not fish. There are these animals that are where the x is. Okay? So now, Venn diagrams, again, use the Venn diagrams to show that this is incorrect. Let's look how an incorrect syllogism looks like. So draw this, and then you will see why this is incorrect. Okay, let's go. Here comes the solution. All M are S is the shaded area. If all M are S, then the M that are not S are shaded away, like here. Some M are P, this is the X. Some M are P, again, there must be an X, because it's a sum statement, between M and P, but half of the M and P, the right half, is already shaded, cannot be there, so it must be in the left half. And then I have all S are P. All S are P, but now this diagram does not show that all S are P. If all S were P, then this area where the arrow points should be shaded. But this area is not shaded. The S area outside of P. This should be shaded to show that all S are P. So all S should be in the common area with the P. But this is not the case here. It's not shaded. So I cannot surely say that all S are P. This is why this is invalid. The conclusion is not represented by the diagram that I get by drawing the premises. Okay? So Venn diagrams are not only useful for syllogisms, I can do other things with them. For example, I can solve mathematical problems involving sets. Something like here, a teacher is planning schedules for 30 students. 16 students say they want to take French, 16 want to take Spanish, 11 want to take Latin, 5 say they want to take both French and Latin, and of these, 3 want to take Spanish as well. 5 want only Latin and 8 want only Spanish. How many students want French only? Okay, so that's a common kind of little mathematical puzzle, and it's very easy to solve with a Venn diagram. You see you have 3 languages here, right? You have Spanish, Latin, and French. And now you can draw your Venn diagram with these 3 languages and try to work out these things. So do it for a moment. Stop the video here, do it, and I will show you the solution in a moment. Okay, here we are. French, Spanish, Latin, and now we fill in what we know from the question there, from the description of the problem. 5 say that they want to take both French and Latin, and of these 3 want to take Spanish as well. So both French and Latin, and of these 3 want to take Spanish as well, means I have 2 in this area between French and Latin, and I have 3 in the area that also includes Spanish. And then I know 5 want only Latin, so I can put a 5 into the Latin box. And I know that 8 want only Spanish. I can put an 8 into the Spanish box. So now if you didn't do it before successfully, you can stop here again and try to solve the rest of it. Now it should be easy, right? Since now all Latin are 11, you know that 11 want to take Latin. And we already have 5 and 3 and 2. If you add whatever we have in the Latin circle, then it means I have only 1 left, who is Latin and Spanish. And without French, and this is 1 person, so I have to put it there so that my Latin adds up to 11. And all Spanish are 16. 16 want to take Spanish, so we already have 8 and 3 and 1, which is in the Spanish circle, which makes 12. So 4 are missing. We write the 4 in there. And therefore, since we know that all French are 16, we already have 9. So there's 7 missing. So 7 want to take French. Alone. Only. And this is the solution. This is the answer, what the question was asking. 7 students want to take French only. Okay? So that's it. You know, I hope, how to do that. If not, go back, do it again. We have some more exercises here. Make a Venn diagram to show whether the following thing is correct. All Greeks like to be in Greece. All people who like to be in Greece spend their holidays there. Some people who spend their holidays in Greece are Greek. Try to do that. Is this correct? Now, you will see if you do this, this is a little difficult, right? Because all P are M, all M are S, some S are P. Now, if you try to do this, all P are M, means that the P that is not M is empty. All M are S. If all M are S, then all M that are not S are empty. And now I can ask, some S are P. But you see, it doesn't work, because a sum statement must be encoded with an X, right? I must have an X somewhere to show these sum. So if this was the solution, it should have an X, but it doesn't have an X. So the conclusion does not follow from the premises. It's invalid. Now, why is it invalid? It seems right. It seems right. Why is it wrong? Because the root of the problem is that there might not be any Greeks at all. Nobody said that there are Greeks. If we had an additional premise, there are Greeks, this would put an X into the central area and the syllogism would be correct, because the S, no, who is the Greeks? The P is the Greeks. So now, if I had a statement, there are Greeks, then, or some people are Greeks, then I would put an X to the P, and since all P except this little bit is already known to be empty, the X would go into this little empty bit that is pointed to by the arrow, and then the whole thing would be valid, right? So the problem is we just don't know if there are any Greeks. So you have to be aware of that. In principle, look, every syllogism that has premises with only all statements and a conclusion with a some statement must be invalid, because in the Venn diagram the sum is an X. If you want an X for the conclusion, you must have an X in one of the premises. If none of your premises gives you an X, because these are all type premises which result in a shading but not in an X, then you cannot have a conclusion with a sum, with an X, right? These will necessarily be invalid. So if you want an X in the conclusion, you must have an X in the premise. If you want an all in the conclusion, you must have some all in the premises. Otherwise, you will not be able to prove it. Okay. So again, let's look at this. All vertebrates reproduce sexually. All vertebrates are animals. Conclusion, all animals reproduce sexually. Can you try to do that? Stop this here. Okay. So here, this is not valid because this area should be shaded where the S is, and it is not. If you don't understand why, go back, try to look at it again, this whole explanation. Okay, so we talked about necessary and sufficient conditions, categorical syllogisms, what can go wrong with them, and about Venn diagrams and how to understand syllogisms. Again, like always, if you have any questions, write me an email, or even better, come to the tutorial session so that we can discuss it directly. You can ask your question there and I can do it live with you. I can show you on screen how to do the problem, and this will be then easier to understand than, if you just ask me the question by email. Okay? So, thank you for the moment. That's it. See you next time. Bye-bye.